Hello and welcome to the AP Statistics 2014 number 6 solution video. Let's take a look at what we got here. First, I see a scatter plot with length in inches and FCR, which I don't know. So let's read the premise here. So Jamal is researching the characteristics of a car that might be useful in predicting the fuel consumption rate, FCR. That is the number of gallons of gasoline that the car requires to travel 100 miles under conditions of typical city driving. So it's just how efficient the car is with gasoline for 100 miles. So FCR, we're going to be using that. The length of the car is one explanatory variable that can be used to predict this. Graph 1 is a scatter plot showing the lengths of 66 cars plotted with the graph with the corresponding FCR. One point in the graph is labeled A. So there it is there. Jamal examined the scatter plot and determined that a linear model would be a reasonable way to express the relationship between FCR and length. And a computer output is shown below. So we have all this data down here. Just real briefly, I know they don't ask us to go over this, but in order to determine if this scatter plot, like a linear model would be good for this scatter plot, he would have had to put the regression line on there, look at the residuals to see if there was a pattern or not a pattern, which I can see this would have been nice and even pattern on the residuals. Or he could have looked at the normal probability plot and looked at that as well. So any of that would have worked. But anyway, I just like to go through those on some of these videos to remind people of what would have been done, right, if they would have asked you to do it. Okay, so let's go to the question. So we have our printout here. I can see the equation. They do it for me already. I don't have to put it together. They do have R squared there and the root mean square error. Remember, root mean square error is just an average residual. So if I look at the range at any one location, this is like from 3 up to 6. So that's like a range of 3, which if you kind of take a quarter of that, you're going to get your 0.9 kind of. Like if I went from the center and went 0.9 up and 0.9 up and 0.9 down and 0.9 down, that would include all my data, like 2 standard deviations, but in this case, it's 2 standard errors. Anyway, just those are side notes. Let's get to the real question. The point on the graph labeled A represents the car of length 175 inches. Right, I can see that right there. And an FCR of 5.88. I can see that right there. 5.88 and 175. Calculate and interpret the residual for the car relative to the least squares regression line. Well, they haven't put the regression line on there, but that's okay. I have my equation. So they want me to just take this 175 and put it into my equation to find out what the prediction was. So I'll put 175 in there, calculate that out, and when you do that, you'll get 4.92. So they're predicting like maybe 4.92. You can see that's right about here. So I'll put a little X instead of a dot so we don't confuse them. But you can see the prediction would have been right there, but my real data point is up here. Well, the difference in those two is my residual, right? That's your residual. So that's what they want you to calculate, is what's that residual. Okay, so take your real data point, 5.88, subtract the prediction, 4.92, and you will get 0.96 as your residual. So that's part A. Let's take a look what they said. You can see that right there. So for a car with a length 175, they put it in the equation, they get their 4.92. Then they want you to take the actual minus the predicted and get your residual, and then you're done. Now you see how they put all this in context. You always have to have your context. Don't just chicken scratch it on your paper like I did in the front. All right, here we go, part B. So this is a lot of reading on this one. Sometimes you get these type of questions, so you just got to keep moving. Jamal knows that it's possible to predict a response variable using more than one explanatory variable. Now, this is something that is really tricky for a lot of people, where they're going to take the residuals. You'll see on these graphs that these are actually the residuals from the previous graph, and then they're going to put a new explanatory variable on that. So it's like they're doubling up on the explanatory variables and doing it more than once. You can do this in statistics where you put multiple variables on a graph to try to hone in on making this variation as small as you possibly can. If this was like functions, you think of it as like a composite function where one was embedded in the other, and you'd keep going. So he wants to see if he can improve the original model of predicting FCR from length by including a second explanatory variable in addition to length. So this is tricky. He's considering including engine size in liters or wheelbase, the length between the axles, in inches. So graph 2, we can see this is engine size of the 66 cars, and then graph 3 is the wheelbase. And both of them are on the residuals of the regression of FCR on length. So let me flip this back over. So again, remember I said if you wanted to do the linear model check, you'd have to do residuals. So you have to imagine taking every single residual on here and making those kind of the Y values. So if you were to graph that out, all those residuals from a line that went through the center of this, you would have kind of your evenly distributed thing like this. So what they're going to do is take all of these Y values on the Y-axis back here, and then introduce a new X-axis variable to add onto it to see if they can improve the variation. They want to reduce variation as much as possible. Remember, that's always the goal when you're doing regression and you're trying to make an association, is to reduce the variability as much as you possibly can. Okay, so in your mind, that's really tricky, right? But let's see what we actually have to do. Maybe it isn't as hard as we think. So don't get bogged down, just keep moving, right? All right, so in graph 2, it's the one on the left, the point labeled A corresponds to the same car whose point was labeled A in graph 1 on the front side. So the measurements for the point A are given below. So they give me all my measurements. Circle the point on graph 3 that corresponds to the car represented by point A. Okay, so they're giving me the wheelbase. I don't really have to do a lot of work. I just have to find it. Here's 93. Remember, we had a residual of like 0.9 on the front. I calculated that. So you have to find, for a wheelbase of 93, find where the residual was 0.93, which is right there. Okay, so that's not too bad. There is a point on the graph 3 labeled B, so I see that there. It is very close to the horizontal line 0. What does that indicate about the FCR of the car represented by point B? Okay, so just like any other residual plot or any other graph, if I am close to that line there, right, close to that residual line, that means my predicted which was on the regression line, and my actual were very, very close. So that's all you want to mention. It's nothing new. It's just that you have to word it in the right way. So it's like the predicted value of residual of length, right? This is the residual of length prediction on wheelbase, right? Is very close to the true value, right? So the prediction and the true value are very, very close. It's hard to word that properly. Let's take a look at how they worded that in just a second. Let's do that right now. Okay, so sorry. So part 1, the point with the wheelbase of 93 inches, blah, 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 is circled here. So we circled the right point. And then here's their part B, our part 2. So point P corresponds to a car with an actual FCR that is very close to the FCR that would be predicted for a car with a length by the regression model, which predicts FCR using the explanatory variable length. So we're using length, right, as our explanatory variable. So the actual FCR is very close to the predicted FCR. And that's really all you need to kind of get in there, and you're okay. But we are using the explanatory variable length. Okay, so let's look at the rest of this. We got a couple more questions. Part C. Write a few sentences to compare the association between the variables in graph 2 with the association between the variables of graph 3. So this is a direct, let's just compare the association, right? Compare association. So you should be thinking about big 3, center shape and spread, and also unusual features if you have any. But we're just mostly like, we want to see the difference in these two. So let's look at these two graphs. Right away, I noticed that this one does seem to have a pattern, which means that we were able to reduce the variability a little bit more by putting engine size on it. Here, my residuals are still just scattered like they would have been in the beginning. Remember that on the front, the residuals from the original graph would have been nice and evenly spread out. This graph looks almost exactly the same. Nothing changed by putting wheelbase on it. Okay, this graph, it kind of took that residual graph and improved it by adding engine size. It made a pattern. It made a pattern on it. So in order that variation we used to have has now been decreased. So we have a better fit. So we want to include that. But you can talk about the big 3. So this has a positive trend to it, which means we reduced, or we kind of improved the model. This one doesn't really have any trend. It really doesn't look like it has an association or correlation. Not a good linear fit. This one does look linear. This one does not. I mean, it could be linear, but there just isn't an association to put a linear model on it in the first place. So it does have a positive trend. It looks linear. This looks like it improved the model. This one does not. So those are things you want to mention. The variability that this one has is the same as the residuals we used to have, so there's no change. The variability on this one has decreased from what we had previously, so it's an improved model. So those are the kind of the things you want to include in your write-up. Let's see what they had. Okay, it says graph 2 reveals a moderate association that is positive and linear. Okay, in contrast, there's a weak association that is positive and linear in graph 3. I don't even know if I'd say it's positive. I would say it's just not very good correlation. They would take that too. The association between engine size and residual is stronger than the association between the wheelbase and residual, right? So it's stronger, means it's a better fit. Too many papers. Here we go. So last question. Jamal wants to predict FCR using length and one other variable, engine size or wheelbase. So based on your response in part C, which variable, engine size or wheelbase, should Jamal use in addition to length if he wants to improve the prediction? Remember, this is a composite. It's a double up. We're using length for sure, but we also want to use either engine size or wheelbase. So which one of these two should we use? Well, based on what we said before, right, we know that this is an improvement, so we would like to use engine size as well as length to improve our model. Wheelbase will not improve our model. It will not reduce the variability, but engine size will improve the model and reduce your variability. So that's the one we should use. So let's look at what they said on the solution guide. So right here, engine size is a better choice than wheelbase, right, which is what we said. It has the stronger association and indicates the engine size is more useful than wheelbase for reducing the variability in FCR values. That remains unexplained, right? So this whole question is getting to the coefficient of determination. The coefficient of determination says when you put an explanatory variable on something to get a regression, how much what percentage are you reducing the variability? So if I have variability in my y values to begin with, I put the explanatory variable on there and it reduces the variability now because I only have to look at a little section of it instead of looking at the overall total variability of the y. So by adding a second variable onto it and doing what we did here, I'm increasing that variability even more. So we're reducing the percentage of variability you started with, gets reduced by some percentage, and then gets reduced by another percentage to give you this, what we ended up with here. So reducing, that's the coefficient of determination. That's kind of the heart of it. All right, that's it for now. Ask questions if you got them.